Good morning, good afternoon, and good evening to the Friday talk show with Global Electronics, and this is your host Rajiv Kulkarni. Right now, the time is 8:01 a.m. Central Standard Time of US and 7:30 p.m. in the Indian Standard Time. And today's date is November the 14th, 2025, and we are bringing you every Friday a different topic on electronics manufacturing to support to create awareness among the electronics manufacturing processes, the challenges, the trend, and also the quality aspect of electronics manufacturing. We bring various guests from the industry expert so that they can share their wealth of knowledge to our young budding engineers or the process engineers or the people who are already working in the electronics manufacturing sector so that it can benefit out of this particular talk show, which is a live show every Friday, happens to 30 to 45 minutes, and people are free to approach me if they want to participate, if they want to present any particular topic of their interest, but limited to electronics manufacturing. So today's topic is very interesting topic that we have. It's challenges and limitations from NPI to production in micro HDI, that is high density interconnect in the PCB design or in the processes. So what kind of challenges that we face in this particular aspect, that is what we are going to address. And to talk to us today we have the industry expert or the design expert in the PCB market segment or in the electronics market segment, I will put it this way, Mr. Amba Prasad, who has wealth of experience more than 4 decades in the electronics manufacturing sector. So Mr. Amba Prasad carries wealth of experience. As I mentioned, he is based out in Silicon Valley of India, which is also called as Bangalore, which is a city based in southern state of India called Karnataka. And Bangalore is highly, I would say, dense in terms of technology activities. So let's welcome Mr. Amba Prasad, the veteran of the electronics manufacturing processes. Welcome to the show, Mr. Amba Prasad. Good evening. How are you this evening?
Yeah, doing good. Last week we had a training session successfully in Madras. So
Okay.
that was a very successful session. And
Okay.
yeah, go
Great.
to full
Great.
size.
Great. So you keep traveling and you keep addressing certain issues in the industry, that I'm pretty sure, and
Yeah,
that is why I want to let the audience know that Ms. Amba Prasad is our one of our esteemed guests. Most of the time, he brings so many years of experience in various topics in the electronics manufacturing. So you probably see him quite often on our channel. But the intention of Global Electronics is to share the wealth of knowledge that we have earned in all these years, 4 to 5 decades of working. So it's always said that giving is sharing is giving, right? So we are sharing our wealth of knowledge and it's like a giving back to the society. So let's welcome Mr. Amba Prasad. Amba Prasad, let's start our today's topic,
yeah.
challenges and limitations from NPI to the production. Okay, here is the first slide. Are you
Sorry.
able to
Sorry
are you
about
able
that.
to see?
Yeah,
Here is the first
yeah,
slide.
yeah. I'm
Yeah.
able to see.
Okay.
So the main challenges. Okay, till last week we covered about V curve and all. Left of the curve, right of the curve, and bottom of the curve. And especially many people appreciated that. So then I thought it is much better that after all the theoretical bombardment of information, let's come down to let's step back and come 2 notches down and discuss about what are the challenges and the limitations we face in converting ultra HDI successful NPI runs to a mass build. Need not be to Ultra HDI, it can be applied to any other product, but it becomes more pronounced in Ultra HDI because people go to Ultra HDI itself as some sort of a niche product. And a niche product, after working, if we fail to convert into mass run, it's a huge setback. So
Okay.
that being the case, always we say the leading edge is the bleeding edge, and who dares wins sometimes. And sometimes the people don't want to take a risk because they are afraid of the failures. So these are
Yeah.
the few things I'm putting a few jargons here and there. But there are limitations when we have a successful NPI. NPI builds we have done maybe when we made about 50 models. The Ultra HDI, it can be Ultra HDI as a whole, or can be a large PCB where some part of the PCB is Ultra HDI. It need not be a sort of a Ultra HDI standalone. There can be a few Ultra HDI features built into a main PCB. Nowadays, it is happening everywhere. So these are the gaps. Then it is a fraught with challenges. When I say fraught with challenges, it is not fought. It is not a spelling mistake. Fraught is also a terminology. So in fact, I double checked it. And then actually it has to be about process stability, scalability, yield stabilization, supply chain readiness, and DFM gaps. In spite of left of the curve, right of the curve, shift left, shift right, stay in between, still the problems remain. And then
Yeah.
procedural limitations often stem from insufficient early stage validation. Okay, we were supposed to do a shift left, but in spite of all these efforts, certain things may miss out. There can be a few skips, or there can be limitations or repetitions. So we forget it, and generally it happens that a particular team works on NPI, and the same team will hand it over to mass run. It need not be okay. It can be two separate teams working. There can be a technology transfer gaps and all. This is what it happens. And lack of standards. Sometimes standards don't keep pace with the state of the art, and the people always go for a non-registered or a leading edge practices to prove proof of concept. But then
Yep.
when it comes to mass build, it bites. It bites at the wrong time, wrong place at the wrong time. This is
Yeah.
the whole problem. And yeah, this is what it is. Yeah, I have listed. We have total about 8 slides. Maybe we can go to 4 slides and then we can
Yes. We
take a
can.
gap.
Yeah. We
Yeah,
can. We can. Yeah.
yeah,
So
yeah.
here is the
Continue.
second one. I
Second
have
one.
this.
So the challenges are process stabilization. When I say process, it is CAM process and PCB fabrication process, including assembly. Yield and reliability, and maybe repeatability also comes into picture. Repeatability, via reliability, especially the mechanical integration of the via. We go for a HDI vias. They're very mechanically, they have to be very stable. Though they are signal integrity, power integrity friendly, they are the weakest part in the design, or the sort of a weakest link in the design when it comes to mechanical stability, especially, yeah. And then material behavior. Material behaves very well in NPI build, and suddenly when we go for a mass run, it behaves in a different way. And yeah, supply chain readiness, a PPAP part, and production approval process, which itself is a highly bureaucratic, and it is a technical as well as bureaucratic and techno-bureaucratic. So this is something bureaucracy creeps in PPAP. A lot of pressures, pulls, procedural limitations, panelization and learning. When I say panelization and learning, we generally do NPI in a very small panel, and suddenly we scale to a large panel. When we scale from small panel to large production panel, there all this whatever I told in the beginning, all 1, 2, 3, 4, 5, 6, whatever I told, they repeat often when we try to do panelization. So it is that simple. When we panelize, it might have worked successfully, but all these action items, either individually or collectively, or they everything may gang up, and the envelopes starts moving in different directions. And data normalization, especially when we go to digital twin and industry 4.0, data plays a very important role. And the process window definition. The process window is very tight. You try to fix somewhere, it starts leaking somewhere else. So this is a very tight situation. And again, the last parting shot I gave last week,
Yes.
telling CTQ versus CTF conflicts. That
Yes.
conflicts will creep in anywhere. Yeah, these are the challenges. Next slide. Yeah, I have just taken a production panel of a high density PCB. This is a ODB++ screenshot. You can see one PCB is kept east-west configuration. Other PCB has been nestled into west-east configuration, east-west and west-east. They have nestled two PCBs in one uh, fabrication panel. To me, it looks like some sort of a rigid flex PCB. You can see a rigid portion in green color and flexible portion in pink color. Yeah, generally, when we do NPR run, when we put a very two PCBs or four PCBs in a panel, but when we scale up to do in a mass build, suddenly what was a two or a four may become 16 or 20 or sometimes 40 PCBs in one panel. That's where the problems are really manifold.
Okay.
Yep.
So the key challenges in Ultra HDI transition.
Yeah, process scalability. That's what I told. I told we can put four PCBs in the panel and make it work. And suddenly, when we put 40 PCBs in the same panel, some PCBs in the corner or some PCBs in the edge, behave differently from the PCBs which were there in the center or on the other edge. So there are methods to control this, but in spite of all good efforts, sometimes things go wrong. That's why when it comes to Ultra HDI PCBs, people still put less PCBs per panel, say when compared to a sort of a true PTH PCBs. So
Yeah.
this is one of the limitations. And NPI builds often rely on a specialized low volume process, a niche process, example, laser drilling, sequential lamination, that may not scale up economically across the regions and across the continents. Like we may build some in some other country, due to some reason, we may migrate the production to some other country or localization sort of things. Suddenly, you have to pay a heavy price for that. Or even it can be a time penalty, they can be a technology penalty, or it can be a penalty in terms of sometimes, there is always a challenge to buy or build,
Yeah.
which I can translate it to whether we have to import it or we have to localize it. So localization has been a challenge even in all industries, not only in PCB, even automotive, aerospace, all industries. Though we say localization we have to do, but it's a huge challenge. Number one.
Right.
And Ultra HDI features like sub 30 micron lines and spacing and especially stacked micro vias. Staggered is okay, staggered works, but stacked micro vias demand extreme precision. Scaling this without yield loss is very difficult. That's why the leading aerospace manufacturers and even IPC for that matter, the task force, when they made for a stacked via, they don't recommend more than a four layers of stacking. So you can stack only four layers stacked via. That the reliability task force, they told four layers, four levels will translate into 5 layers. More than 5 layers, they say don't
Wow.
stack because
Wow.
via will they slip into the next layer. So
Yeah.
that's the problem. This is a limitation today. Yes.
Okay, let's take a quick break here and we'll come
Sure.
back.
Yeah.
Good morning, good afternoon, and good evening, and welcome back to the Global Electronics Friday Talk Show with your host Rajiv Kulkarni. So, we bring this Friday Talk Show every week to educate, to create awareness within the electronics manufacturing processes. The basic idea of this particular talk show is to share the wealth of knowledge that we have gained over a period of several years of in being in the industry, and our goal is to bring the expertise from the industry and share the wealth of knowledge to all the people who are concerned and who can take the advantage of the knowledge being shared. With that said, we have today Mr. Amba Prasad, who is a veteran and also is highly experienced in the electronics manufacturing processes as well as the design aspect of it. Mr. Amba Prasad, welcome back after this small break, and let's continue our presentation here. And today's topic is challenges and the limitations on the NPI build to the production build in the Ultra HDI interconnect industry. So let's continue our discussion.
Yeah, I think there is one pop-up window is blocking the main screen. Yeah, now go to next
Yeah,
sheet. Yeah.
yeah,
So, okay,
yeah.
Rajiv, I just wanted to say somebody asked Kennedy about what is democracy. He told of the people, by the people, for the people. Again,
Yeah.
global electronics is by technology, for technology, and of technology. Maybe we can just use that. I was just
That's a good
correlating
one.
this when you were
That's a good.
telling. So yeah, again, key challenges in Ultra HD transition. Again, I'm processing the way first I started with the design, and now I'm going to vias and material. Now, if we get into material, early prototypes may pass functional test but fail under thermal cycling. CAF is a major threat, and mechanical stress and in a mass build. And via reliability, stack is versus staggered. I told about the number of
Yeah.
layers, what can go for stacking. It becomes a real bottleneck when moving lab scale builds to production scale. And electrochemical migration. So electrochemical migration occurs when the component is assembled. This electrochemical migration, what we are talking is not uh, a sort of electrochemical migration, what we discussed very earlier. This happens between the adjacent, let's say we have a BGA, very fine pitch BGA. The adjacent BGA bumps, they see some electromigration between them. This is a very nuanced subject. Sometimes people confuse this with a dendrite or something. One is electrochemical migration, one is electromigration. So there are two aspects here.
Two
So
aspects. Yeah.
electromigration is also there. Yeah, electromigration can happen. Electrochemical migration can happen, and CAF will happen in the inner layer, and dendrites will happen in the external layer. And also there is one more threat, foreign debris. When people do testing or when the people do assembly, uh, they do any dicing or this kind of operations, simulation operations, some small dust particles or some even solder particles, they may fall within the gaps, and this becomes a major threat. And this is never ending process. This process was there and this process continues. This always happens. One has to be very, very careful. Let's go to the next page.
Yeah.
Supply chain readiness. We talked about PPAP. So vendors may not be all equipped with a laser direct imaging. So laser direct imaging nowadays people don't depend on films anymore. It is a direct laser plotting on the cores and things like that. And added to the confusion in a PCB, what we are trying to do, we might have put a insulated metal substrate as a thermal management scheme, and that plays another role. That can be a very big challenge. These are the challenges, and since it is a multi-layer structure, hybrid stack-ups, and these kind of things, it's very difficult to predict, especially the CTE mismatch in the vertical direction, Americans call as a z-axis. So this is a very major, it's very difficult to predict, and people have to really simulate and do design of experiments and come back. And qualification of multiple, just one slide back. Qualification of multiple suppliers is very slow. Industry as a whole doesn't want to depend on a few suppliers. As a plan B, we may have to go for a very a group of suppliers, but approving each supplier or approving a separate material or a separate material with the same supplier, same supplier, new material set, or a different supplier, same material, and different supplier, different material. So there are so many, it's like a huge hydra-headed monster. It is like a arm wrestling with an octopus. You have only 2 hands, octopus has got 8 hands. Octopus wins. So
Yeah.
that's the whole problem. Okay. The next page. I
Yeah.
think after this we have only one more sheet. I
Yes.
have
Yes.
few
Yes.
slides
Yeah.
here.
That's fine. We are good. Yeah.
So
Yeah.
in the agenda, I showed a data normalization at the end, and the next slide topic I showed before that, but I thought I have to reverse it. So because if we prove it as a data, be it say a digital twin or even Industry 4.0, even last time I was talking about a digital triplet or a rogue runaway twin. So runaway twin either doesn't give the data what you want, or it gives the data what you want, which is wrongly interpreted. So
Okay.
that is another runaway twin. You start believing the figures. The figures
Yes.
are not there, but it gives the figures. Maybe due to wrong entry or wrong assumptions or whatever. Some
Right.
people call it as a triplet. Some people call it as a runaway twin. So this runaway twin is a very dangerous situation. We start believing what we are seeing. So that's
Yeah.
the whole problem. Data normalization, design data from multiple sources, EDA tools, fabrication notes may be inconsistent without a neutralized, standardized data sets. Misinterpretation leads to scrap. Generally, when it comes to fab notes or a specification sheet, many people tend to copy paste. They copy paste without knowing, or they copy paste from a successful project to a new project. Okay, I have done this project, I am successful. So let me take the data set from this project to the another project. It may not
Yeah.
be.
They try to implement
Yeah,
the
yeah. This is
same.
the
Yeah.
so this is the one major process where this is the crux where your runaway digital twin is going to be born. So that is the problem. It is lurking in the corners. We don't know. It is always there. And the process window definition. Ultra SDA process have a narrow process windows, etching, plating, lamination, and via alignment. It's very narrow. It is a few microns actually.
Yes.
Sometimes what
Yes.
happens, the
Yes.
feature size itself maybe 10 to 20% of the deviation. So let's say in a regular PCB we may call off a deviation of a few microns, but here a feature size itself can be one third of it or half of it. It will not properly. This is another big headache. And then NPI builds cannot successfully characterize this. We might not have captured in NPI. We may not have thought that it is going to be a large panel or something. leaving gaps in statistical process control. I mean, basically, here I'm trying to capture where your runaway digital twin is coming. It
Right,
works in
right,
simulation. It doesn't work
right,
in the real build. Yeah, one
right.
example I can give you. For example, when we do a very highly specialized Ultra HDA PCBs, we do panelization. One successful way to avoid warpage in a panelization, let's say you have 16 PCBs in that. I'm just giving an example.
Yeah, yeah, absolutely,
Arrange
absolutely.
16 like a chess block. Then in this block, you put half PCBs facing up and half PCB facing down in the panel.
Okay.
That is a very short medicine to avoid warpage. Because one PCB tries to warp in a smiling direction, another PCB tries to warp in a frowning dimension. Now there are two sets of PCBs in the opposite direction, and one tries to smile, one tries to frown, and they stabilize each other. But it is very easy to say, theoretically, this is one of the best solutions available. Many companies have followed, but it is a nightmare. You have to have two separate sets of stencil screens, two separate sets of programs, two separate sets of test probe boxes and all, and it's a very costly remedy. But it works actually. Many times, sometimes it works. This is the last resort. Many companies have invested on this and have successfully succeeded in that. That's one. And let's go to next sheet.
Oh, I think we are done.
I think there's one DFM and DFA gaps.
Oh, here it is. Yeah.
You have to just go. Yeah.
No,
Last
I think there was one blank here. Yeah, here it is.
Yeah. Key challenges in HDI
Yeah, that got cut.
transit.
That is, yeah,
DFM and DFA gaps.
yeah.
So this is basically what we are going to cover in the next session of how to control these things. But here I'm just giving a curtain raiser. Sort of people can see what comes next.
Yes.
Many NPI designs are optimized for a proof of concept only, not manufacturability. Without early concurrent shift left DFM analysis, issues may surface only in ramp up. So this is one. The shift left is one of the solutions. And then it should have a, don't, there are set of standards. All the standards are cross-connected. Be it IPC standard or an international standard, or IPC standard with the international standard. So IPC standard starts as a base, then they start deviating. There can be addendums, and IPC standard can be referred by the international standards. But they're cross-connected in a very subtle way. When we cross-connect these standards, if you don't cross-connect properly, again it becomes like a wrestling with an octopus. That's a big problem. So you try to fix somewhere and somewhere it opens up. So this cross-connect is very important. A class-wise, item-wise, we have to cross-connect these standards. And in my opinion, if someone removes unimplementable and repeatable attributes, it is good. That's the one shoot shot solution. That's good. And then panelization and yield learning. This I told, it works in a small panel. It doesn't work in a big panel. So the panelization, don't jump into panel immediately. Even for a production panel, we may have to do some sort of an ad hoc mini NPI run there and then go. I mean, it is a mass build, medium build, and large build. I mean, NPI, a medium build and large build. It really works actually. It works very good. Yield learning is a very much important yield learning. And then NPI builds often use a single panel run. So this is what I have told. Mass builds require optimized panel utilization, coupon placement, and test structures, copper balancing. Whole lot of issues are there, which are generally unique to what a PCB vendor or a assembly house does on the handling area. So in as a handling area, they do this kind of features. They have a very good but nowadays a lot of third-party tools are available which simulate this, and to a certain extent it is being addressed. So industry knows that there is a problem. And
Absolutely.
scaling introduces new defect modes. Registration drift, H ununiformity rather than H uniformity, H ununiformity, lamination warpage, all these are new things which are coming. And there are three classic defects which come by the material itself. Maybe in the next section I try to
Session,
cover.
yeah.
Yeah. So that's
Excellent.
all I have to say. And one thing is, this keeps the industry running. Challenges are there.
Yes.
Veterans are still having currency in the industry. New tool sets are coming, and new algorithms are coming in third-party tools. Yeah, this is developing. Things are still in a developmental stage. That's all I
Absolutely,
have.
absolutely. Very well presented, Mr. Amba Prasad, and thank you very much for your time. And um to all the viewers out there, I definitely thank you all for taking your time and to watch this show. Because of viewers like you, definitely our channel is able to slowly grow, and we are just past 1 year of our starting of our channel. We started last year in October, and we have completed 1 year. And we would request you to increase our subscription so that more the subscribers, more the viewership, and better for the audience as well as the speakers out there who would like to come and join Global Electronics to share their wealth of knowledge to the electronics community. Whether you are based in Europe, you are based in China, you are based in India, or in the North America or South America, it doesn't matter. The channel is meant to share the wealth of knowledge that we have gained in the last several decades. So Ms. Amba Prasad is a veteran, as I mentioned earlier, based out in Silicon Valley, that is Bangalore of India, and has wealth of experience in the design and also consulting, and his IPC CID trainer, and so he trains a lot of engineers out there on a regular basis. With that said, I would like to conclude today's episode, and then definitely we'll come back with another new topic next week at the same time and on your channel Global Electronics Friday Talk Show with your host Raju Kulkarni. Till then, please take care of your health and be happy and have a wonderful weekend. Thank you all. Thank you very much. God bless.
Thanks.